Hello and welcome back to Erudite. In this video we're going to explore how we can use the breadth first search and depth first search algorithms to find a path between two nodes or 2 points in our network. So what we're going to do is actually just take this piece of code that we wrote in the previous video, in the depth first search and breadth first search video. We're going to copy it into a new file because we're going to make some edits to this. First thing we can do is just get rid of that link, and we can change this to say a program script to explore pathfinding using, I think it says the breadth first search algorithm. Yes, lovely. Okay, so that's just set up the start of our file. And now what we're going to do is we're going to adapt this algorithm a little bit so that we can firstly check if there is a path between two nodes, and then if there is a path we can find that path and return it. And we'll just start with breadth first search. So let's relabel this search and we'll just tidy up our search a little bit. We'll add a start and end argument and we'll change this to start. It's just a little bit tidier, a little bit smaller. And what we can do is actually bring these both into one line. So we can just pull things together a bit neater, like so. We want to say if node is equal to end, return visited. So if we've found our endpoint, we don't bother continuing with the search, because if we had had a huge network and two nodes were basically next to each other, we don't want to have to traverse the entire network just to return that yes, they are connected, when within the first sort of iteration of the search we've already found them. So this just allows us to exit and return the visited. And then we do the normal thing: if node not in the visited and node not in queue, we just append it and then we continue with this. And if we continue with this all the way through and never return here, we know that we've never found the endpoint. So actually what I want to do then is return an empty list, which of course will read as false in Python. So we can use a sort of if true statement or truthy statement. So that's changed our search a little bit, but now we want to add a new function. And we're just going to do a super simple function to begin with. We're going to define an isPath function. And any of these ones that start with is, I believe the convention is normally that they're going to return a true or false, because you're asking the question, is there a path? You don't need to know the path at this point, you're just saying, is there one there? And you'll get a true or false output. And they're usually really nice little simple functions. So we're going to pass to this the start, the end and the network. And in fact, nearly all of these things are going to go into the search, because we're going to call the search with if search start, end and network. If that's true, so it returns a value, we're going to just return true. And that will mean that our isPath function will say yes, there is a path. And if it's not true, if we don't exit the function here, then we can just return false. If you're more comfortable, you can put an else here and then take that into an else statement just for the red logic of that bit of code, but that else is completely unnecessary really, and you can just do this. So let's save that, and what we're going to do is see if there's a path between two of our nodes, and try and remember what I called it. No, not that one. There we go. So Python calling BFS find path. What have I forgotten? I meant to put isPath. Sorry, I'm getting ahead of myself. There we go, isPath. And it's saying false. Why is it telling me? I put these two the wrong way around. I'm sure you caught that when you were watching and were wondering why on earth I hadn't fixed it. Well, there we go. Now that's fixed. Let's save that and run it and see. Now we get true. There is a path between A and G. And just for fun, we're actually going to make an non-connected node into here, and we'll check that. But before we do that, let's just clear up the terminal. So if we add an extra node, let's call it X, and it's only going to be connected to Y, and we'll see if A is connected to X, and this should return false. Perfect. So what we're going to do now is actually write a function to return the path instead. So we'll call this find path. We'll have a start, end, and a network. And we're going to use the the search function, which is it returns the visited value. So visited is equal to search, start, end, and network. And within that search, remember that if it finds the endpoint, it returns the list of visited nodes, so that we can work back from that to get our path. But if it doesn't find anything, it returns an empty string. So we can add a little function into here just to tidy that up for if nothing returns. If visited, we'll just pass that for now. Else, return, and we can do a nice little F string, no path found between start and end. As before, we don't actually need that else, so we can tidy that up a little bit. So we'll go find path. So let's just run this and see what we get. No path found between A and X. Now we want to use the visited to find out what our path is. So our path is going to start with the end point and work backwards, finding the first time when a connected node to the endpoint was discovered. And then we'll just keep chopping the visited a bit shorter until we get back to the start. And that'll actually give us the path running in the opposite direction. So it'll give us the path from the endpoint to the start point. So what we want to do is we're going to, within a while loop, just carry out an iterative function where we work our way through this visited list, generating our path. So we're going to say while start is not in the path, keep doing something. So we'll just put pass here for a second, and then we're going to say return path. So when we exit this, when the start is in the path, we return it. And that's our whole, then we know that's the whole path. So within here, we're going to want to have a function which we're going to call something like build path, and it will need to take the path that we already have, the visited that we'll edit, and the network so that we can see the connections. And in fact, it's going to alter the path and visited values each time. So we want to make sure we output from this build path function a visited and a path. So let's have a look at how we can code this up and think about the way we need to iterate this visited list that we're going to have of nodes that we've been to. So as we go to each node, we want to work back, finding the first time that a connected node was visited. So if we had gone to, let's do the A to G one here. So G, when we're at G, the first time we find D, the only thing connected to G in our list of visited, we want to go to D, add that to our path, and delete everything that was seen after it, because we don't care about that anymore. And then what we want to do is we want to look at the things that D can be connected to, B and G, and of course we'd actually have deleted the G connection now because we've got rid of that N bit. And the first time it finds anything in this list as it's going through, that's the quickest connection that could be made. So we'd then hop to that position and delete everything else that was seen. So we're going to write up a little bit of code to do that, and hopefully it becomes clear as we write it. So we're going to have to look at the nodes in the visited list, but we're also going to want their index. So we're going to need to enumerate this list. If a node that we find as we're going through this list is in the network, so we're referring to that network dictionary or that adjacency list at path -1, so the last value we added into the path, if that node is in anything connected to that last value or last node that we added to the path, then we need to append it to the path, and we need to slice the visited so that we get rid of everything at the end and we don't look at that anymore. And then we can break because we found the next thing in our path. And after we've done that, we can return the new path with the added value or the added node and the new visited that's been sliced. And that's how we'll iterate through this until we've found our start position. We've got back to our start position. So let's run this and see what we get. Oh, I've got the A to X, and we know that that doesn't give us a path. So let's do A to G again. And we'll just tidy this up and then run it again. So and remember this is in reverse, this path. So it's telling us that G goes to D, D goes to B, and then B goes to A. And that's the shortest path that we have between A and G. So that's working really nicely. Now it might be really bothering you that the output of this is the path in reverse. So we're going from end to start rather than from start to end. Now of course you can easily do this by just using the reverse function on the test, the output, that you get. So in this case it would be test. But you can also use the insert function here, and we'd put that at 0. So it's pushing each value into the beginning of that list. But we've got to be quite careful because here we're referring to the position at the end of the list. So if we do it like this, it will just keep looking at the same value. So then we need to tell it that it always needs to be looking at the first value. So if we run that, it gives us the list in reverse, A, B, D, G. So now that we've put that back, we can of course check other things like H to G and see how that looks, and we can see that we've got this really nice route. Now, a little challenge for you is to apply this to the depth first search algorithm, and I'm just going to leave it like this for a second and then I'll show you the solution to that. It is almost identical, and all these files, by the way, I meant to say this and I keep forgetting to say this, are on GitHub. If you want to pull these out and have a little play with them, feel free. And if you have, when you're looking at this going, why on earth doesn't he do this thing to improve the efficiency? Let me know and I'll have a look at it. I'll give you a moment to have a go at the DFS. You can pause the video and then we'll have a look at my solution. And so here we have the depth first search. The network map is the same. I've just changed this title up here to depth first, to explore pathfinding with the depth first search algorithm. And then down here we've got our search function, and as before, can you remember we don't need to use the DEC or DQ data structure for this one because we just append things to our stack, so it's not necessary. So we removed that import. And we also just changed the labeling of Q to stack. Pop became pop instead of pop left. And we added this little bit here with the if node is equal to the end, because we added the end argument. Then we return our visited, otherwise we return empty string. The isPath method is identical. There's no change whatsoever, because if this search returns something, then we know there's a path. If it just returns an empty list, we know there isn't. So that's super easy. The findPath method is, I believe, identical, because once again we use that visited, so all of this structure is pretty much the same. We take our path, we start at the end point and we work backwards along the list list of visited to see what was the first instance of a connected node, to find that shortest path. And then we use the same method of build path to iterate through, building up our path one node at a time, using exactly the same method down here, and let's see if it works. So I'm going to save this. I've got the breadth first search I have set up here with A and G, and the depth first search version I have set it with A and G, and they should give identical results because they should both find the same shortest path, even though they go about it in a different way. So let's check, or let's get the breadth first search value up here. So that's GDBA or ABDG the other way around. And for depth first search, let's get that going. Find path. Voila, identical. So you can see how it's super easy to extract a path using this algorithm. Really very, very simple and very efficient coding as well, because you basically use the same procedure that you do to test if there is even a connection between two nodes. You take that visited set and you can easily unpack it to return your path. So it's a really, really useful tool to have, and we're going to explore in the next video visualizing this. I did think I was going to do it in this video, but I'm always concerned that they get quite long, especially when a visualization's involved. If you found this video useful and you enjoyed it, please give it a thumbs up, maybe subscribe to the channel, and thank you so much for watching. Hopefully I'll see you in the next one. Bye!